Our speaker shouldn't really need any introduction, but just in case you missed who Juan Maldacena is, I'll tell you a few words. Anyway, Juan got his undergrad degree in Reloj in Argentina. Yeah, I shouldn't even try to say this. Bariloche. In Argentina, then he came to the United States, has been here ever since, landed at the Institute of Advanced Studies. And if you haven't heard about ADS-CFT, please go have a look. No, it's kind of important, and he's the one who wrote it down. And we are very happy to have him here and kind of give us a talk about magnetic black holes.
Okay, thank you for the kind introduction. I met Steve only a few times, unfortunately, and talked to him very briefly. Of course, he was the embodiment of authority, I would say, for all the works he had done and his, voice and appearance. Now, in thinking about this talk, I thought I'd talk about some aspects of magnetically charged black holes in the Standard Model, which use in a very interesting and crucial way the Weinberg-Salam theory. So this is based on a paper of a few years ago. And in this context, I'll also discuss work by several other people. And I'll use this to say, to also review how recently quantum gravity effects are enhanced for near extremal charged black holes. And this is a subject where there was a lot of work recently and leads to a solvable sector of quantum gravity. And so and these extremal charged black holes give us a possible road to explore some aspects of quantum gravity in the lab with a little fine print, which is that if you're lucky enough to find these magnetic black holes. So motivation is that magnetic black holes are long-lived configurations compatible with the laws of physics we know. All we have to assume is the U1 is compact. Normally, I normally have to assume some other laws of physics, supersymmetry, and so on. But in this case, the assumptions will be just the Standard Model with a compact U1. And there are interesting primordial black hole candidates. And they have interesting and surprising properties because they have large magnetic fields. What are these interesting properties? First, they are a natural way of generating large magnetic fields in the sense that you can have a huge magnetic field that does not decay and so on. The electroweak symmetry can be restored around the black hole. And fermions lead to a large number of effective fields around the black hole. I should emphasize that I'm talking about black holes with monopole charge. So they have magnetic monopole charge. They can catalyze baryon decay. So it's similar to the Callan-Ruoco effect. And we can approach extremality and see some quantum gravity effects. And you can have very light black holes, let's say 1 kilogram black hole, and it can be very long-lived. So these are some of the interesting properties. I'll kind of review all these properties and explain some of these aspects. So let's start with black holes. So the usual Schwarzschild black hole will evaporate before the age of the universe if the mass is less than roughly the mass of a mountain, as you probably all know. Now, if you have charged black holes should have masses bigger than some number times the charge. And when the mass is close to the charge, then we call them extremal. And those black holes have very low Hawking temperature. And the black hole, a charged black hole like this, if it emits only neutral particles, it will get to extremality. And that will happen if all the charged particles are very heavy. And then it will cease to evaporate. Now, we can ask whether they exist or whether there are bounds on their number. Now, before we discuss those questions, we have to do step 0, which is to understand some of the properties of these black holes. So let's start with the simplest charged black hole solution. This is the Reissner-Nordstrom charged black hole solution. And so it's similar to the solution for the Schwarzschild black hole. It has a function. Oh, wait, happened. Yeah, maybe I should just point with the pointer. So this is the usual, the metric of such black holes. I took here the metric just of the extremal black hole, so at 0 temperature, mass equal to the charge. We have some magnetic field on the two-sphere. And the flux of the magnetic field on the two-sphere is quantized. And so the black hole is characterized by an integer, which will take always to be much bigger than 1. There is a characteristic scale, which is the size of the black hole. It's given in terms of the charge and in Planck units. So we would like this to be much bigger than the Planck unit, so Q will be large. E is just some number of order 1, it's 0.3. But for the purpose of this talk, think of it as a number of order 1. An electrically charged black hole would have a very similar metric. However, in nature, we can easily create electron and positron pairs that will discharge this black hole unless the black hole is very big. So if you have a really big black hole, like a size of 10 to the 5 kilometers, then it will not create the electron-positron pairs, but anything smaller than that will discharge. And that's even in the vacuum. Of course, if you are not in the vacuum, it will discharge even more quickly. But magnetically charged black holes are more interesting because they are stable if magnetic monopoles are very heavy. So if you have magnetic monopoles whose mass is of order of the grand unified scale, then these magnetic monopoles are very heavy, and so they will not discharge a magnetically charged black hole. And I emphasize we're always talking about black holes that have magnetic monopole charge. In these black holes, the magnetic fields are very large, and they lead to new effects. So before we discuss these new effects, we will need to see a quick reminder of how charged particles behave in magnetic fields. So let's imagine we have a magnetic field orthogonal to some plane, and then we have, of course, Lorentz symmetry along the direction of time and the direction of the magnetic field. And a four-dimensional massive particle will give rise to some particles that move along the directions of the magnetic field with an effective mass that will be the four-dimensional mass plus the energies of some Landau levels, right? So we can consider the lowest Landau level for particles with various spins. So spin 0, so let's say the simplest case of a spinless particle, then the orbital angular momentum of the particle going around the magnetic field in its lowest energy state will give us an energy of order the magnetic field. So that's very familiar. In the case of a half particle, then there is a possible cancellation between that orbital energy and the dipole magnetic moment. So, and you can have a zero energy. So you can have perhaps that could precise cancellation. And if you had a charged particle with spin 1, then well, I guess one point I should have mentioned here is that this cancellation for massless particles, it's precise and it's due to an anomaly, to the chiral anomaly. This case of spin 1 is relevant for the W boson. In that case, the magnetic moment overwhelms the orbital energy, and you can have a negative energy if this mass is small enough or if the magnetic field is big enough. So that means that if we have a very big magnetic field, there will be an instability where we can start condensing the W bosons. Now, of course, there are further other levels. So all the other Landau levels give further energies, but we will not consider those. Now, the magnetic fields are very high in this black hole. So the field strength is Q over R squared. And when you are in the near horizon region, this R squared is, well, it's given by the formula we saw before, which when inserted gives us something of this order. So the magnetic field gets weaker as Q becomes larger, but it starts out being of order the Planck scale. So you can have fairly large Qs and still have pretty substantial magnetic fields. So for example, that electroweak instability that we had discussed before will kick in when the field strength is of order the mass of the W squared, and that corresponds to a very big magnetic field. But when you translate to what kind of black hole that would be, it would be a black hole which has a size of roughly 3 centimeters. So if you have a 3 centimeter size magnetically charged black hole, you already have this issue. Now, when the charge is smaller than this charge, this charge we talked about here, and the black hole is smaller, then this magnetic field becomes larger, and you'll condense these W bosons. Okay. Now, we expect that this condensation of the W bosons will screen the SU2 part of the magnetic field. So in the standard model, the electromagnetic field consists of a piece that is along the U1 of the hypercharge, so the U1 group of the standard model, and a U1 inside the SU2 part of the standard model. And so the idea is that we cancel this SU2 part by the W bosons, and we get only the hypercharged magnetic field. The Higgs will be charged under the hypercharge. Oh, unfortunately, we had this funny, I don't know what that means. And so the contribution to the total mass from the lambda level of the Higgs, so we remember that for spinless particles, we had positive mass, positive contribution. That means that in the Higgs potential, we had originally a negative contribution around the origin, but this gives a positive contribution, so the Higgs will be driven to 0 for large enough magnetic fields. So electroweak symmetry is restored for sufficiently large magnetic fields. And all of this was analyzed many years ago by Ambjorn and Olesen. There is the following phase structure. So if you are in flat space and you start increasing the size of the magnetic field, what you find is that if the magnetic field is not very big, we have the usual vacuum with some magnetic field. That's what we usually have in the lab when we have magnetic fields. But if we increase the magnetic field up to the mass of the W, then we get some phase with non-zero W bosons, and the Higgs is also excited. And if the magnetic field is big enough, then we have purely hypercharged magnetic field, and the Higgs will have 0 BeV. Okay, and that happens when the magnetic field is bigger than the mass of the Higgs squared. So we have this kind of mixed phase here, and this phase is not uniform in space. You get a lattice of vortices, and as I said, this was analyzed many years ago by Ambjorn and Olesen. So these magnetic black holes give us a natural situation where we have these large magnetic fields. So now we go back to the black hole case. And so we have a black hole whose size is smaller than those 3 centimeters that we discussed. And there is a lot of charges we can have. That charge that gave 3 centimeters was enormous. So there is a whole range of charges we can have and smaller black holes. And such black holes have a region far away where we have the usual electromagnetic vacuum, and a region closer to the horizon where we have a vacuum where the electroweak symmetry is restored, and then this funny phase with the vortices further away. And so we can call this the electroweak corona. So it's similar to the solar corona that is dominated by the magnetic fields. And also it's a nice name because it was during the time of coronavirus. Where these kind of shapes were all over the place. Okay, so as we said, it's not quite spherically symmetric. For very tiny values of Q, for example, Q equal to 1 or 2, then they are spherically symmetric, but for larger values of Q, they are not. And in general, we don't know the precise solution. These authors have looked at some axisymmetric solutions. They are not expected to be the minimum of the energy, but those are some examples of precise, exact solutions of this kind. So this is presenting similar information. So here on the horizontal axis, we have the charge of the black hole and the corresponding mass. And we have the black hole radius and the radius of this region where the electroweak symmetry is restored, the electroweak corona radius. So for example, here, if you had a black hole of a mass, let's say of a few kilograms, then this this corona radius could be, between the bigger than the size of the proton and smaller than the size of an atom, roughly. So something fairly big. As I said, if you make the charge very big, this could be a macroscopic distance where you have the electroweak symmetry restored. Okay, so far we described the classical solution, but once you put in the matter fields, there are some interesting aspects also. The fermions are all massless in the region where the electroweak symmetry is restored, and they're all charged under the magnetic hypercharge field. And so they all have a zero energy Landau level, as we discussed, and which is highly degenerate because we have the degeneracy is proportional to the total magnetic flux, which is that large charge that we were talking about. And this leads to massless modes that move along the radial direction, and they can be viewed as moving along the magnetic field lines. You basically have one massless mode per magnetic flux quantum. So it's over an area which is of order 1 over the size of the magnetic field. So you can write down all the fields of all the fermions of the standard model, where there are quantum numbers and so on, and you can figure out how many each of them gives rise to either a purely left-moving or purely right-moving massless field that will move along the directions of the magnetic field. And so you get this number of fields. So it's important that in all cases you get some number which is proportional to the charge of the black hole, so a large number. Now, all of this happens within this corona. When we cross it and we go out, then all these fields get some mass. Some get more mass than others. The neutrino becomes neutral, so you don't have this Q degeneracy. And in principle, to find the proper infrared dynamics, we also need to consider the dynamics of the gauge fields and how they interact with these massless fields. This has been somewhat studied by some authors, but I think it's not completely understood. Now, this large number of fields leads to corrections to Hawking radiation. So if you look at how these black holes would emit Hawking radiation when they're at finite temperature, you would find that they're given by the two-dimensional Stefan-Boltzmann law, so proportional to t squared. And there is a large factor due to the large number of effective fields that we have of order Q. And this number should be compared to, let's say, the formula for a Schwarzschild black hole. So for a Schwarzschild black hole, we have the 4D Stefan-Boltzmann law with t to the 4th, and then an area factor, which the area is related to the temperature. So in the end, you also get something proportional to t squared, but there is no factor of Q. So the amount of energy that is emitted in Hawking radiation is greatly enhanced in this magnetic black hole case. So just to give you an idea of this example, so let's go back to an uncharged black hole of a mass of a mountain. That's the 10 to the 12 kilogram black hole, which would take an age of the universe to evaporate, right? And now consider exactly the same black hole, but let's say with magnetic field. And let's say it's order 1 deviation from extremality. So let's say a mass which is twice the charge, just to give an example. And then the evaporation time, according to these formulas, would be of order milliseconds, so much faster. So much more quickly, we go back to extremality. So these black holes can also catalyze proton decay. So black holes violate global symmetry, so baryons can go in and leptons can come back out. So it can lead to that. So it's similar in spirit to what happens with the Kallan-Rubakov effect for magnetic monopoles. I mean, many of these effects are in some sense present also for magnetic monopoles. It's just that these magnetic black holes are sort of magnetic monopoles on asteroids. Much bigger effects. In addition, you could also have Spaleron effects that aren't suppressing the corona, which could also lead to baryon number violation. So now, are these black holes completely stable? So the answer is no. So even when they decay all the way to 0 temperature, they could decay by pair creating other magnetically charged particles. So they could pair create, for example, even singly, so smaller black holes, or GUT-like, grand unified-like monopoles, or even lighter magnetically charged objects. So exactly how stable they are depends on what the mass of the magnetically charged objects is. And if you assume that the only magnetically charged objects are these grand unified monopoles, then you can conclude that black holes with charges bigger than about 1 million will be effectively stable. And these would be very tiny black holes of order the masses of order a gram or so. So more things of this order would be effectively stable over the age of the universe. Now, so all of this is very nice, but you can ask, well, could this ever be produced? Could this type of black holes ever be produced? And the answer is that it is impossible that they are produced, but not quite impossible. So these are very exciting and interesting objects, but we should be realistic and think that they're quite difficult to produce. So let me just remind you of how people think that maybe black holes could be produced in the early universe. So this is just producing neutral black holes. So this is relatively easy. So you can have, for example, large primordial fluctuations at some scale. So we know primordial density fluctuations are small at long distances, but at perhaps shorter distances, you might have some more violent fluctuations that could lead to the production of black holes. So that's one mechanism, or you could have phase transitions or violent processes after the end of inflation that could also produce black holes. So these are well-known mechanisms. Now then you can ask, well, can we produce magnetic black holes in the early universe? Now, you can do that by something one can call the square root of n mechanism that was also discussed by these authors. And so the idea is to imagine that, again, you have a situation which is after the end of inflation, we produce a large number of monopoles and anti-monopoles. And then in addition, we have these large scalar fluctuations that will produce black holes. The black holes will swallow most of these monopoles, but there will be some fluctuations in the charges of these monopoles. And if you think that the fluctuations will be of order square root of n, then you could imagine that some will have a little bit more negative charge and some a little bit more positive charge. And then in this way, you could produce black holes which will have a little bit of a tiny bit, well, let's say a small charge compared to their mass, but then they will evaporate and give rise to extremal magnetically charged black holes. So this is a very qualitative mechanism that you could imagine perhaps something like this could work, or maybe one of you will think of a more realistic mechanism. Now, of course, this is not the simplest that we would expect. This is not what we would expect in the simplest models of inflation. And there might be other mechanisms for producing such black holes. Now, there have been some studies constraining their abundance, their possible abundance, and the constraints you find are similar to the constraints you find for magnetic monopoles. So this is an example from one of the papers. The precise bounds depend on some assumptions you make and so on. And so these bounds, you can write them as a fraction, the density of these magnetically charged black holes over dark matter. There is a well-known bound, it's called the Parker bound, that, for example, tells you that dark matter cannot be all magnetic monopoles. So that's an old story from the 80s, I guess. So this applies also in this case. And then you have some other bounds from these black holes getting into white dwarfs and destroying them, and various bounds of this kind. So the bottom line is that they are, so especially the light ones of, let's say, masses of order. Here the mass is in grams. So if a few kilograms that we were talking about, they are not very abundant. We already have very strong constraints, even regardless of the production mechanism. Okay, so these are, I think, fun objects to think about. And I will also use them as an excuse to talk about quantum gravity. So among the various interesting features of extremal black holes, one of them is the fact that quantum gravity effects become important. So these are in principle present for any near extremal black hole, not just these magnetically charged ones. But in nature, these effects would only be observable for these magnetically charged black holes. Yeah. So for electrically charged black holes, these effects are negligible. Now, maybe there are other black holes in the dark sector that might lead also to quantum gravity effects. That depends on the details of the dark sector. But from the standard model, the only black holes that could lead to these effects are these magnetically charged ones. So the idea is that magnetic black holes can be very close to extremal, and they can lead to quantum gravity effects becoming important. Now, I'm not going to discuss these quantum gravity effects in detail. So if the black hole, if the charge is large, you would have a weakly curved space-time everywhere. And you might think that the quantum gravity effects will be small and proportional to, let's say, 1 over the charge, or more precisely, 1 over the charge squared. So they will be small. However, as you go to extremality, the geometry develops a very long throat, and that throat can fluctuate. So it can become longer or shorter. And that's a mode that can become strongly coupled and lead to strong quantum gravity effects, even for very large charges. Okay. So how close to extremality is this effect important? So this was understood, this type of effect was understood a long time ago. And it's important when you get to temperatures of order. So remember the scale 1 over RE that had to do with the size of the black hole. So these are sizes much, much smaller, or temperatures much, much smaller. Sorry, size is much longer, so the temperature is much smaller than 1 over RE by a factor of the order of the extremal black hole entropy. That's a factor of Q squared. So this is how it scales with Q. So it's a very tiny temperature. However, let's say for a black hole of 10 kilograms, so we have a 10 kilogram magnetically charged black hole, this scale is of order of a few EV. Okay, so it's a kind of lab scale. So this is something. It looks like a tabletop experiment, something you could do on a tabletop, right? Of course, if you need to first find these magnetic black holes. I don't what? Yeah, there is some issue. I'm hiding some things. You need a magnetic field of I think it's about 100 Tesla in order for it not to fall in the gravitational magnetic field of the Earth. So maybe you need to put the tabletop in space, but anyway, so it's well, it sounds something manageable if you found the black hole. I mean, if you find the black hole, you could definitely do this. So now some good news. So about this quantum gravity mode is that it can be quantized exactly. So I said that there were some large quantum gravity corrections, but in the last few years, we understood how to quantize this particular mode that becomes strongly coupled exactly. And so we can calculate whatever you want about this aspect of quantum gravity. It's really genuine quantum gravity in the sense that it's a fluctuation of the geometry of space-time, of the length of this throat. And we can find the precise formulas. I will not describe them in detail, but it leads to falsifiable predictions for quantum gravity that you can verify using tabletop experiments. Of course, there is the detail, fine detail. Anyway, I should also emphasize that this activity for quantizing this mode, okay, I presented it here based on the line of these magnetic black holes, motivated from magnetic black holes, just to give it a more, fit more standard model basis, appropriate to the Weinberg Center. But it was motivated by condensed matter physics problems where there is a similar mode and a similar degree of freedom, and there are some symmetries that are in common between some condensed matter physics problem and these near extremal black holes. Okay, so let me give you just a very simple example of correction of this kind. So if you calculate the two-point function of fermions at different times in the vicinity of these black holes, they would scale like 1/times at short enough times, but at very long times, so times longer than this temperature scale and time scale we were discussing before, they will go like 1/t³. This particular power law is a prediction of this strongly coupled quantum gravity theory. We have the full function of how this changes from here to here. That's the prediction we were discussing before. Okay, so in conclusions, magnetic black holes are very interesting objects in the standard model. They have this magnetic corona. They lead to enhanced Hawking radiation, enhanced proton decay, enhanced quantum gravity effects. Unfortunately, they are harder to produce than magnetic monopoles. So all these exciting things, but that's a bit of a downer. But there are other questions we can ask. Is some phenomenological? Maybe there are some more production mechanisms. Maybe there are more constraints from astrophysics. And there are some also theoretical questions. So understanding properly the infrared dynamics with large magnetic fields, I think it's an interesting theoretical problem. Okay, thank you.
Do you have any more questions other than the ones Juan asked himself?
Yeah, Catherine? Here. Oh.
How big does the magnetic field have to be in terms of Gauss to get rid of the Higgs wave?
It was something I think about 10 to the 20.
If we're being practical here.
I think it was 10 to the 20. I had it here. I don't remember.
Oh, you did? Okay.
Yeah. So it's the biggest magnetar has something like 10 to the 9 in some units. This is 10 to the 20 in the same unit.
No, 10 to the 14.
10 to the 14?
Oh, you're talking Tesla.
Tesla, yeah.
That's why I asked.
Yeah, sorry.
Anything else? Well, if not, we can thank our speaker again.